section on the tangent line, the derivative, and instantaneous velocity. This first video is going to hit the learning target of finding an equation of the tangent line to the graph of a function. And hopefully you'll notice that a lot of the things that we talk about here, when we did the AROC-IROC unit, you'll see a lot of overlap between those between these two units. All right, so these are going to be the other learning targets we do. So again, we're just going to start with the first one here. So follow along, try the examples. If we're about to do an example, see if you can do it on your own. So pause the video and then try it, and then click play again and see how well you do with the example. All right. So the tangent line. So recall that the average rate of change of a function from the point x f of c to the point c f of c is given by the expression. Again, hopefully you remember this from when we studied AROC. And that's just going to be f of x minus f of c all over x minus c. All right. And so again, I'll just draw it up here. If we had some function, here's the point x, here's the point c. This would be f of x, and this would be f of c. Right? We're talking about the slope of the line that connects these 2 points. All right? And so that's your AROC. If you recall, that is also the slope of the secant line. So slope of the secant line. Okay. So the secant line is the line that connects the points x f of x to the point c f of c, with the slope of the secant line being the average rate of change between those 2 points. And so what's going to happen is, as our point C gets closer and closer to x, or vice versa, as x gets closer and closer to c, our average rate of change gets closer to that 0 over 0, what we've been seeing with our limits. And so when that happens, we can't evaluate, right? 0 over 0, we don't know what that means. So when x equals c, we can no longer describe the average rate of change and the secant line. Instead, we're going to move to the tangent line. And so the tangent line to the graph of a function y equals f of x at a point P, where P is the ordered pair C f of C, on its graph is defined as the line containing the point P, whose slope is given by m of tangent. Well, it's now a limit, right? So it's going to be the limit as x goes to c of your secant line slope. So I'm going to do m secant, which is really, we're going to take this and we turn it into a limit now. So it becomes the limit as x approaches c of f of x minus f of c all over x minus c. And so we're going to have to evaluate this limit. That will give us the slope of the tangent line. If we know the slope of the tangent line, we can then write the equation of the tangent line. And so that takes us to our second point here. If m tangent exists, again, this may not exist. Okay, again, this may not exist. An equation of the tangent line, we're going to write it in point slope form. Y minus f of c is equal to your m tangent, which you're going to find using the limit definition up here, times x minus c. And so that will give us the slope of the tangent at the point c f of c. So we're going to take a try at this first example. We're going to find the equation of the tangent line to the graph f of x equals x squared over 4 when x equals 1. Right, so hopefully you tried this. So the first thing we want to do is find the slope of the tangent. Okay, and so the slope of the tangent is going to equal the limit as x goes to, it's going to equal the limit as x goes to 1 of my slope here, right? And so f of x is x squared over 4 minus f of c. F of c is the output of plugging in 1. So f of 1 is 1/4 all over x minus 1. And again, you see here, if you plug in the 1, you get a 0 over 0. That's your clue, right? That's going to indicate to you you need to algebraically manipulate this so that we can evaluate this limit. All right, so if we evaluate this, let's rewrite this as the limit as x goes to 1. I'm going to have x squared minus 1 over 4 times x minus 1. So I rewrote this with one denominator. So that's going to equal the lim as x goes to 1, factor x minus 1, x plus 1 over 4 times x minus 1. And now you should see that the x minus 1s cancel, right? They divide to 1. And so now you're going to get x plus 1 over 4. I can now plug in my 1. And so we get 2 over 4, which is 1/2. And so the slope of the tangent at x equals 1 for the function x squared over 4 is 1/2. Now, if I want to write the equation of the line, I'm going to use point slope form. I already know what f of c is, right? We know that's 1/4, so we can just write y minus 1/4. We now know the slope of the tangent at that point is 1/2 x minus 1. And so this is our tangent equation. All right, so again, you're going to set up the limit, right? Using our AROC, the limit's going to go as x goes to c. Evaluate, you're most likely going to get 0 over 0. Algebraically manipulate so that you can plug in what x is approaching, and that will give you the slope of the tangent. Then from that, plug it into point slope form. Right, so now we're going to look at example 2. Once again, try this on your own. See how you do with it, and then when you're ready, check through my solution. All right, so if you tried this, given f of x equals the square root of x, complete the following. Write an expression involving a limit for the slope of the tangent at x equals 4. So we're going to use the limit as x goes to 4. My function is square root of x. Now I'm going to evaluate it at 4. So f of 4, right, f of 4 is the square root of 4, which is 2. So minus 2 over x minus 4. So that is the expression involving a limit for the slope of the tangent at x equals 4. So now we're going to evaluate that limit. Now I'm going to do this a slightly different way, just to introduce something that you may not have seen before. Chances are you multiply by the conjugate, which is absolutely fine. That'll work here. I'm going to do something slightly different. I'm going to actually factor x minus 4. So even though this isn't in the a squared plus b squared, I'm going to kind of force it to be in that form by rewriting it as this. The limit as x goes to 4, the square root of x minus 2. I'm not touching that. And then now, instead of x minus 4, I'm going to rewrite this as the square root of x minus 2, the square root of x plus 2. So this is still, like, if you think about it, this is our perfect square, difference of two squares form, right? If I FOIL this, I'm going to get square root of x times square root of x to get x, negative 2 root x plus 2 root x. My inner and outer terms cancel. Negative 2 times 2 gives me that negative 4, so I get that exact same value. The reason this is nice, because now I can just go like this. Those cancel. Put a placeholder of 1. Now I have no issue plugging in a 4. So the limit as x approaches 4 of our slope of the tangent is going to be 1 over root 4 plus 2. And so we get 1/4. 1/4 as our slope. Okay, so the slope of the tangent is 1/4 there. Again, you should get the same exact answer if you multiplied by the conjugate. All right, and then I did some algebraic manipulation. Hence, write the equation of the line tangent to f at the point where x equals 4. All right, so again, we already know that f of 4 is 2. Now we just plug it into point slope form. Y minus 2 is equal to 1/4 x minus 4. And there is your slope of the tangent.